Have you ever just stopped and noticed the hidden rhythms playing out all around us? From the way a tree branch sways to the steady tick-tock of an old clock? Well, it turns out there's a mathematical pulse beating under the surface of it all. Today, we're going to peek behind the curtain and uncover the simple, elegant code that governs that rhythm. I know, it sounds like a weird question, right? One's a tiny little thing you can hold in your hand, the other's a massive building. But get this. They and a ton of other things are basically dancing to the exact same physical tune. And today, we're going to learn how to read the sheet music. So to really get our heads around this universal rhythm, we've got to start with the basic physics. Turns out, there is one secret ingredient, one key force that makes this whole dance possible in the first place. Okay, let's look at the classic example, a mass on a spring. See that dotted line there? That's its home base, its equilibrium position, its happy place. Now, when we pull that mass down, we've moved it away from that happy place. We call that displacement x. The whole system is out of balance now, and it really wants to get back on. And that wanting to get back, well, that's what physicists call the restoring force. And this is the absolute key. It doesn't matter where the mass is, if it's stretched way out or compressed way in. This force is always, and I mean always, trying to pull it back to the center. It's like a tireless guardian of balance. So how strong is this force? Well, it follows this beautifully simple rule called Hooke's law. Basically, the force, F, is just proportional to how far you've pulled it, X. That K is just a number for how stiff the spring is. But see that little minus sign? Oh, that is the secret sauce. That's the math way of saying the force is a rebel. It always points in the exact opposite direction of where you moved it, trying to drag everything back to the middle. Okay, so we have a force. That's great, but how do we turn that into, a description of the actual motion over time? For that, we need to write what I like to call the master code of oscillation. And this is where the power of physics really shines. We start with the big one, Newton's second law, F equals ma. Then we just swap out the F with our special restoring force from Hooke's law. So now we have mass times acceleration equals minus k times x. Then we just do a little bit of algebraic shuffling and bam, we end up with this incredibly powerful equation. This right here, this is the heart of our entire explainer. It's the differential equation for what we call simple harmonic motion, or SHM. Now, I know it might look a little intimidating, but just think of it as a rule book. Any system that follows Hooke's law has to obey this rule. And that omega symbol, omega, think of it as a single number that packages up the spring stiffness and the mass to tell us how fast the system naturally wants to wiggle. So we have the blueprint. We have the rule book. The next logical question has to be, what happens when we solve this thing? What does the answer, the actual path of our bouncing mass, look like over time? And the answer is a sine wave, a beautiful, smooth, endlessly repeating wave. You've seen this shape a million times. This equation tells us the exact position x of that mass at any moment in time t. This wave is the signature, the fingerprint of simple harmonic motion. And this is where it gets really useful, because this one little equation lets us decode the whole thing. A is the amplitude, that just tells us how big the bounces are. Omega is the angular frequency, that tells us how fast it's bouncing. And that last one, delta, the phase constant, that's just the starting line. It tells us where the mass was when we hit the stopwatch. Now, all this theory is great, but physics really comes alive in the real world. So let's see how this code works, and sometimes needs a few tweaks, when we're dealing with actual stuff. So in our perfect textbook world, springs don't weigh anything. But in reality, of course they do. A real spring has its own mass, and because the spring itself is moving up and down, it has its own kinetic energy. And that means our simple model is just a little bit off. The actual bouncing is going to be slightly slower than our ideal model says. So, how do we fix it? Well, engineers use this really clever idea called effective mass. It turns out, after some pretty neat calculus, that you can fix the problem just by adding 1/3 of the spring's own mass to the main block. It's a simple little correction that makes our predictions way more accurate. But oscillation isn't just about bouncing up and down. Let's switch gears and look at something totally different, the torsional pendulum. In this case, you've got a disc hanging from a wire. You don't stretch it, you give it a twist, and it just oscillates back and forth, rotationally. And this is where we see that universal idea I was talking about. Just look at the math. The structure is identical. Linear up and down motion x just becomes rotational twisting theta. Mass m becomes I, which is rotational inertia. The spring constant becomes a torsional constant. But the master code, the fundamental equation, is exactly the same. It's the same rhythm, just a different kind of dance. So we know how these things move, but what's the fuel? What's powering this whole rhythmic back and forth? To answer that, we need to talk about energy. In this game, there are two main players. You've got potential energy, which is the energy stored up when the spring is stretched or squeezed. Then you have kinetic energy, which is the energy of pure motion. And the most beautiful part is that in a perfect system, no friction, their sum, the total energy, is locked in. It never, ever changes. The energy just gets passed back and forth between these two forms. And you can see this energy dance perfectly in this graph. Look. At the very top and bottom of the bounce, the mass stops for a split second. At that point, kinetic energy is 0, and all the energy is stored as potential. Then, as it zips through the middle at top speed, the spring is relaxed, so potential energy is 0, and it's all kinetic. It's this seamless trade-off. While that flat line up top, the total energy just stays perfectly constant. And here's a fascinating little fact for you. If you average out the energy over one full cycle, one whole oscillation, it's split perfectly, 50-50, between kinetic and potential. It's just another example of the beautiful symmetry that's hiding inside this simple motion. All right, we've looked at springs, we've looked at pendulums, we've looked at energy. Let's just take a step back and really appreciate the big picture we've just painted. After all of that, what's the one big idea that really ties all of this together? It all comes down to this. Nature is incredibly efficient. It uses the same fundamental mathematical pattern, that equation for simple harmonic motion, to describe a mind-boggling variety of things. We're talking everything from the vibration of an atom to the sway of a bridge. It's a universal blueprint for rhythm. And that really just leaves us with a final thought to chew on. If one rule this simple can be so powerful and so widespread, it really makes you wonder, what other fundamental, elegant codes are out there governing the universe, just waiting for us to discover them?